So this is the first time, I think, that I've shown in a presentation the picture of my book, my new book coming out, Modern Software Engineering. And some of the ideas in this are kind of based on that. And I'm going to explore those. I've got a couple of other books that talk about continuous delivery and continuous delivery deployment pipelines also around. Let's start from here. Let's start by thinking about software projects. And I think that if you think about the success of a software project, then if software projects were normal things, we'd expect to see a normal distribution of success. We'd expect to see as many software projects finishing ahead of schedule, under budget, delighting their users, as finished behind schedule, over budget, and annoying their users. But I don't think that's what we perceive of as normal in our industry. I think we normally experience stuff that looks more like the red curve than the blue curve. And I think that says something fairly profound. I think that what that says is that the model that we've got for software development is in some way wrong. It's not normal. It's not working in a normal kind of way. And therefore we should probably think carefully about that model. I really love this little GIF animation of the orbits of the planets in the solar system. This is based on two different models of the solar system. On the right-hand side is the geocentric model of the solar system, where the assumption, this was the model that held for tens of thousands of years, the assumption was that the Earth was at the center of the universe and that everything in the sky revolved around the Earth. People used to think that there were crystal spheres that held the stars and the sun and the moon on them, and so on. And if you look at the sky, then that makes sense when you see the sun going around us and the moon going around us and the stars going around us. And then there are these pesky things called planets. The word planet is derived from an ancient Greek word that means wanderer, because when you pay attention to the night sky and try and figure out what the planets are doing, then they start tracking these weird courses, and sometimes they're going backwards with respect to us, and sometimes they're going faster than they should be, and they're in the odd places in the sky. And it's a very difficult problem as long as you assume that the Earth is at the center of the universe. If you inhabit a solar system that looks like this, then you can't come up with inverse square laws as Newton did, and you can't come up with bendy sheets of space-time like Einstein did. And that means we can't have space rockets and GPS, and we can't even fire bullets accurately, because trajectories depend on models of gravity that Newton came up with. Doesn't make any sense. So living in a solar system on the right-hand side means that there are certain ideas that you can't even begin to think. What this takes is something called a paradigm shift. And I know lots of marketing people sometimes talk about paradigm shift, but this is what a real paradigm shift looks like, in that you change your frame of reference. You change something fundamental about the way in which you understand a problem. In this case, instead of placing the Earth at the center of the universe, placing the sun at the center of the universe. And that's what Kepler, Copernicus, and Galileo did. And that model's wrong. The sun isn't at the center of the universe. It's at the center, but it is at the center of the solar system. And that's good enough to be able to simplify the model. So the model doesn't have to be correct to be better, but the one on the left is a better model. It is significantly more accurate than the one on the right. And the key idea here is that it dramatically simplifies the picture. Even I could do the maths to kind of figure out where the planets are in that second model. It's that simple. The model on the right, some of the most sophisticated machinery up to that point in history was designed to try and figure out where these damn planets were in the sky. So this is the idea of paradigm shift, and I think this is a really nice idea as an analogy for where our industry is. I think that much of our experience of software development is as though we're living on the picture on the right. We add complexity on top of complexity, And that's because we're not getting some of these fundamentals right. We're not thinking about software development in the right kind of way. So what does software engineering really mean? I think that we tend to have an odd model of engineering in our heads. As I said in my kind of lead-in, I think we think about these things in slightly weird ways, and we think about complex things and production lines like these and so on. And this is not our problem. This is nothing to do with software development or the problems of software development. Software is deeply unusual stuff. Software, however big or complex the systems that we build, our output is a stream of bytes, ultimately. And that means that the production for us is simply copying that stream of bytes. Our problem is never a production problem. And our ability to accurately reproduce that stream of bytes somewhere else, let's say deployment, we copy it from a disk somewhere to another disk somewhere where it's deployed and executed. For software systems, that is essentially close enough to be considered free. The cost of production is essentially free, however many copies we make, because it's just so cheap to be able to reproduce this stream of bytes. So production is inherently not our problem. Our problem is something very different. I think that one of the weird things when we as software developers think about engineering is that we tend to conjure up pictures like this. We tend to imagine, massively complicated structures and the logistics of trying to put this kind of thing into place. And when we're talking about physical systems like a bridge like this, then that's a huge part of the problem, maybe a more difficult part of the problem than designing the bridge in the first place to some extent. But that's not our problem, because we've got this ability to freely create things. Our problem is entirely different. Our problem is about the design of the systems, and only that, because once we've designed them, we can produce them for free. I am currently obsessed by following this thing, that this is the SpaceX Starship. This is the first one. This is a mock-up. This isn't one of the ones that actually flew. But Elon Musk and his team at SpaceX are attempting to build the world's biggest spacecraft. And they're getting close. Their next launch will probably be the first orbital launch of this system. Now, one of the things that's really fascinating, if you're a nerd like me, is being able to watch this and see real world-class engineering happening live on YouTube. They're building incrementally these systems. And engineering is not about massive Gantt charts and massive plans. It's about adapting and learning and trying things out and experimenting and seeing what happens, and building test rigs to try things out and carrying out experiments and blowing things up to see at what point they fail, and flying little things that look like flying water tanks to see if you can do that with one rocket, and then blowing more things up because you get something wrong, and so on and so on. Engineering at this kind of level, when you're building something new, is an exercise in exploration and discovery. It's about learning. It's about figuring out what's going on, and how do we solve the problem that we're trying to face. SpaceX don't know all of the answers. They're probably not even close to having half the answers yet, but they're building a body of answers, and they're building a body of reliable stuff that they can make progress with. They now have rockets that can fly and land, and they're building the next level that are about to go into orbit, and so on. engineering is at this level, when we're talking about design engineering, and that's all that software engineering ever is, because production is free, then design engineering in particular is about exploration and discovery, and a little else really. And so I think that what this means, so software development is about exploration and discovery. Because the cost of production is essentially free, then, you know, we'd be foolish to recreate something that we'd already got, that we'd already produced. So we're always doing something new. It might not always be brand new to the world. It might only be new in our context or new to us. But as we are working on it as software development, it is always new to us at some level. So it's always at some level about exploration and discovery, because the cost of production is so cheap, because otherwise we just make a copy. I think that what that means, and deeply, you know, really should inform our discipline, is that if that's the truth, and I think it is, then we should be aiming to become experts at learning. We should be optimizing everything that we do to focus on our ability to learn, and to learn fast, rather like the SpaceX engineers. And for that, we need ideas like iteration. We need to make progress in many small steps, observe our progress in those steps by gathering feedback. We then go to build on what we've learned and make new progress on the next stage. So the SpaceX engineers, they start off flying things that look like a water tower, just short hops, and then they learn from that and they blow some space rockets up, and but they have some successes, and then they move on and they start flying things sort of 12 miles up into the sky and then landing them back. That's how engineering really works. The other aspect of this that's deeply important, I think, if we want to start to claim to be engineers, by which I mean applying scientific, rational approaches to solving practical problems, then we also need to be working experimentally. Each change that we make is a small experiment. We're going to try out that change, and we're going to gather the feedback and going to see whether the change was good or bad, and we're going to make decisions based on that. We're not going to start off assuming that all of our ideas are correct. We're going to start off assuming probably that some of our ideas, maybe most of our ideas, are incorrect. And that means we've got the ability to test to see if it's incorrect and how it's incorrect, and to react to that and to correct it if it is incorrect. That's much closer to engineering style thinking. Some of the early pioneers in software development who talked about engineering in those days talked about focusing on the failure modes a lot. So thinking about how things can go wrong, and thinking about ways to mitigate that. That's a deeply engineering style mode of thought. And we also want to be empirical. We want to be observing the real world. Engineering is a practical discipline. It's not hard science. It's not the same thing as physics or maths. It might use those things as tools, but it's not the same thing. So we're going to learn from reality, rather like the SpaceX engineers. We're going to be making mistakes and hopefully not blowing things up on quite the scale that they are, but we are going to be making mistakes and learning from those mistakes and adapting to them and growing our systems incrementally over time so that they become better and better and better. So retaining our ability to be incremental and to make progress by being experimental and empirical is really important if we want to be able to learn and make progress. I think the other aspect of this is that software development is about managing the complexity of the systems that we build. No complex system springs fully formed from the mind of some kind of genius. It's hard work building complex systems, whatever the nature of them. And the way that we human beings undertake that hard work is to do it incrementally, to build up our learning, to learn and adapt, and to refine what we're learning and to improve things. Sorry, just pressed the wrong key. There we go. So we want to optimize to manage complexity. For that, we need to take some of these these ideas seriously. If we want to manage the complexity of the systems that we build, they must be modular. We need to compartmentalize the system so that we can make change in one place without worrying whether that change is going to leak out and affect other places, or at least minimizing the degree to which change will leak from one place to another. That means that we need to abstract our systems. We need to have seams in the design of our software beyond which we don't really care so much about how it works. We're just going to talk to it through some interface or some abstraction or some API of some kind. We want to be able to separate concerns. We want to have parts of the system that are responsible for doing one thing and other parts responsible for other things. If your code downloads a file from somewhere or other and then processes that file and then stores that file somewhere else, those are three separate jobs, and that code would be better if those three separate jobs were coped with three separate bits of code. And designing our code, even at the fine-grained level like that, is going to improve its quality by separating the concerns in the implementation. We'd like the pieces to be loosely coupled. This goes back to the thing that I was talking about earlier on, that we'd like to be able to make change in one place and not have that change leak out to other places. This is at the core of being able to do software development, certainly on any scale. Sure, if you are working alone, you can probably write bad code and it can be tightly coupled with poor separation of concerns and poor modularity, and maybe, perhaps, maybe you can cope with that. But even if you are working alone, if that code grows to any kind of size and you come back to it later, you're going to be more lost than if you applied this kind of thinking and these kind of strategies to making that code better. And the last in my list in managing complexity is cohesion. This is the degree to which pieces of the code are related to each other. So you could think of these two extremes, modularity and cohesion, as making sure that I'm paraphrasing Kent Beck here, who made a wonderful quote about what high quality design is, and he said that it's moving the stuff that's unrelated further apart and the stuff that's related closer together. And I think that's as good a description of good design as any that I've come across. And that's what modularity and cohesion do. We want to be able to isolate bits of software that are unrelated from one another so that they can change more independently, and use techniques like separation of concerns and abstraction and loose coupling to achieve that. And we'd like within those modules the responsibilities to be cohesive, to be the ideas to be related and not just kind of randomly allocated. So let's start thinking about the principles of applying this kind of thinking to software development. So we need to optimize for learning and optimize to manage complexity. To do that, we need to start taking seriously ideas like taking control of the variables. If we want to become experimental, which was one of my ideas for optimizing for learning, then we must take control of the variables so that we can understand the results of our experiments. If I test a massively complicated piece of software system only in end-to-end testing, then I can't tell very much about it, because it's end-to-end and there's this big, massively complicated system going on underneath me and I can't really understand what's going on. There are too many variables. If I isolate parts of the system and focus on evaluating those, I can tell much more about each of those parts. And then I can do that for all of the parts, and I know much more about the system as a whole. There's more to it than that, of course, but controlling the variables is vital if we want to be more focused on doing a high quality job in understanding and building better software. We'd like to make evidence-based decisions rather than just crossing our fingers and guessing that our design is good, or that our code is good, or that it does the right things. We'd like to carry out experiments on our code and falsify it, prove that it doesn't do the things that it doesn't do, or convince us that it looks like it does do the things that we'd like it to do. So we want to try and make these better evidence-based decisions. I think another of the ideas that's really deeply philosophically important in applying this kind of engineering, scientifically rational mindset is never assume that your answer is correct. Always assume the result, the reverse. Always assume that it's probably wrong and then look for where it's wrong. That's a much stronger way of evaluating your software. Just a simple way of describing that. However many automated tests or army of people testing my software, I can never ever prove that it's good. There's always the chance, there's always the possibility that I've missed something and I'm not testing something important. But if I flip that around, if I say that a single test falsifies my software, if a single test fails, I don't release my software, then that's definitive. This is an old argument that modern science is built on top of. It's the idea of falsifiability, which was introduced to science in the 1930s. And the example that was given was that I can assert that all swans are white, but I can't prove it. But as soon as I see a single black swan, I know that that's not true. So this is the kind of thinking that we can start applying to our discipline. We can use tests as a tool. And that brings me to testability. Testability is one of these key tools that allows us to do a better job. So let's start by thinking what it is that we might value in good code. And I warn you in advance that my list is going to sound familiar. First of all, it has to work. Obviously, good code works. It does something useful and it does that thing. But it's also modular. It allows us to work on parts without affecting other parts, as we already described. It's loosely coupled. We can change pieces of the code more independently of one another. It's highly cohesive. The bits that are in front of us are related so that we can make changes easily and safely. We understand if we change things here, all of the bits that I need to worry about are here, and that's going to help me make change and evolve the code over time. It's going to have a good separation of concerns. Each piece is going to be focused on doing a part of the job well, and only that part of the job. And it exhibits information hiding or implements abstraction to draw these lines between different parts of the code. We've already talked about all of these ideas, but they play double service. They are both the tools with which we can use to manage the complexity in our systems, but they are also the properties that we value in our software. Think just for a moment about two different pieces of software. Doesn't matter what the technology is, doesn't matter what the language is, doesn't matter what problem they're solving. If you have two pieces of software that are solving the same job, and one of them is modular, loosely coupled, highly cohesive, good separation of concerns with great information hiding, and the other one doesn't, the first one's going to be a much nicer place to work, and you're going to be able to manage that, work on that much more effectively. So these are genuine values of attributes of quality in software systems at every level of granularity and detail. So what allows us to put those properties, those high quality attributes into the code that we develop? And I would argue that before test-driven development, just three things: the skill, experience, and integrity of an individual programmer. You have to have the skills to be able to do work like this. You have to think of the ways to design software that is modular, good separation of concerns, loosely coupled, and all of those things. And that takes a degree of experience. You're not going to jump into that on your first ever piece of code that you work. It doesn't work like that. You have to learn these skills, and that takes a while. And you've got to be bothered. If you're not really bothered about this piece of code and you're just going to throw it away, you're probably not focusing on doing a good design job. But if you are, then you're probably going to do a better job. So those are the things that really allow us to put these qualities into the code. I want to talk now about test-driven development, because this is getting to this point of testability. I think that the testability of our systems is a significantly powerful tool that we can use to achieve some of the ends that I've just been describing. Test-driven development is a specific thing. It's not just another word for unit testing. If you write the test after you wrote the code, you're not doing test-driven development. So test-driven development is this. It's often called red-green refactor. So red, we're going to write a test, we're going to run it, and we're going to see it fail. I like to predict the way that it will fail. That's one of the little experiments that I like to carry out when I'm writing a test. Next, we're going to write just enough code to make the test pass. We are currently in an unstable state while the test is failing, and we like to get back to stability by making the test pass in the shortest possible number of steps. So we're going to do the simplest thing that we can to get back to making that test pass. And then, and only then, while we've got a passing test, are we going to refactor the test and the code to make them more expressive, more readable, better factored, more elegant, more beautiful, more generic, whatever it is that we want. This is the real deeper design, the quality design step in our approach. So think about that. If you've never worked this way before, just think about that for a moment. We're going to drive the development of the software from a test. Now, the unfortunate part of test-driven development is it's called test-driven development because it's not really about testing, it's about design. So we're going to design the code from a test. Now, you have to be some kind of weird, strange person to do that in a way that's going to make your life harder. You're going to write a test to make your life easier. That means that you're going to inherently be there's a pressure on you to design the code to be more testable because that's going to make your life easier. So you're going to write more testable code. And then what is it that makes code testable? Well, it has to work. Obviously, the test is verifying that the code has to work. It's modular because we need to be able to test pieces of the code in isolation from one another to be able to control the variables sufficiently to see how things really work. And it's loosely coupled so that I can kind of deal with one part of the system without bringing in lots and lots of other parts of the system and having horribly complicated setup in my test cases. It's cohesive so that the bits that are related are close together in the scope of the test, and I'm evaluating the behavior of my system through that test all together at the same time. It's got a good separation of concerns because we'd like to focus our tests on testing just the behavior in front of us and not worrying about complicated issues like putting things on a display or writing to disk or collecting things out of a database. It exhibits information hiding. So we've got these lines of abstraction that help us achieve this modularity and cohesion. So the attributes of testable code are the attributes of code that we value as high quality, and also the attributes of code in which we are able to better manage the complexity of complex systems. This is starting to sound like a joined up idea to me. So before TDD, we had the skill, experience and integrity of an individual programmer. That doesn't go away. Good people are still going to do a better job than less experienced or less talented people. Sorry, experienced people, skilled people, rather than good people, are going to do a better job. But in addition to that, if we add test-driven development, we also get that amplifying effect of test-driven development, that pressure on us to achieve a more testable outcome. The result of this is kind of a win-win scenario, a kind of exponential growth in the quality of our code. We're able to design better systems and get feedback on the quality of our systems sooner through fast feedback and iteration. Techniques like continuous integration and continuous delivery will give us that, deployment pipelines and so on. And the test-driven development is going to drive quality into our code bases at the fine-grained technical level that we were just discussing. So it has an amplifying effect. It's not going to make a bad programmer great, but it will make a bad programmer better, and it will make a great programmer greater. Let's do a little simple, trivial, worked example of what it is that I'm talking about. Here's a car, and the car has an engine, and this is in this case, it's a petrol engine, and it's got a function called start, in which we're going to put the car into neutral, we're going to apply the brakes, and then we're going to start the engine. So let's write a test for our car. Here's my test. Should start car engine. We're going to create a new car. We're going to say start, and now there's nothing that we can do. The engine's private. So if we wanted to test this, we'd have to break the encapsulation of our code to get at the engine, or do something ugly to try and get at it. Otherwise, we can't tell that the engine starts. So that's not really testable code. So let's only focus, nothing else. We're not focusing on design. We're only focusing on trying to make this code more testable. So here's a better car. And the simple step that I've carried out to make it better is this one. I've used dependency injection to pass in an engine to the better car, and now instead of creating the petrol engine, we just pass in an engine to the better car, and that gives us a very different experience. The code otherwise is exactly the same, but let's try and write a test for this. So here's my test. We're going to create a fake engine. So what's a fake engine? Well, here's my fake engine. All it does is it just records the fact that when we call start, that start was called, and then we can kind of query that later on. In reality, we'd probably use a mocking library or something like this if we were doing test-driven development to build this code for us, but I just wanted to do a simple example, a simple demonstration. So here's my fake engine. We're going to create a better car with a fake engine. We're going to call start, and now we can say, did the engine start? And we've got a test. Just for a moment, think about what that means in terms of the code. I would argue, and have argued earlier, that this is a better car. I even call it a better car. This is a better code than the previous code. And it's better because we've got a better separation of concerns. This car doesn't conflate the ideas of engine and car, other than through the interface to the engine. We've got a more modular code because now we've broken out the engine. The better car is independent, more independent of the engine. It's more cohesive because this car is focused on the carness rather than the engine-ness. The engine worries about the engine functions somewhere else, and so on and so on and so on. What this means practically is that this is dramatically more flexible code. In use, I could decide to create a car as before with a petrol engine, exactly the same behavior as before, but I could also choose to create a car with an electric engine without changing the better car. Or if I'm a crazy person, I could create a better car with a jet engine. And all of these things, my code is more flexible because it's more composable, more modular in design. The next in my list of things to kind of focus on if we want to work more like engineers is working more experimentally. And I'll remind you again, the SpaceX and engineering in the real world is deeply involved when we're thinking about design engineering, about experimentation. This is a very, very early prototype of a thing called a Raptor engine, which is the SpaceX Starship engine, which burns methane. It's an unusual kind of engine, but it's the most powerful rocket engine that people have built so far. And this is an early test bed showing them using it. And then you carry out all sorts of different experiments to evaluate the behavior of your system. Engineering proceeds in terms of these kinds of practical experiments. And that leads us to this idea. We want to make progress in small steps, work incrementally, gather feedback, understand what it is, the changes that we're making, and predict the results of where we're going to guide our experimentation, and learn from our predictions, control the variables within the scope of our experiments so that we can understand the results of the experiments too, clearly and quickly and concisely. Fundamentally, these ideas are at the heart of my preferred approach to software development, which is continuous delivery. In my world, continuous delivery is a slightly bigger idea than DevOps, but many people think of it the other way around. So you can use these terms interchangeably in the way that I'm describing them. But what I'm talking about really is our job is to aim to continuously deliver valuable software into the hands of our users. We're going to have an idea. We want to be able to get that idea into the hands of our users quickly and as efficiently as we can. And we want to learn whether our ideas are good or bad. To do that, we want to do the kind of thing that I've just been talking about. We want to build high quality code so that we can get those ideas reliably and repeatably into production. And so we want to test them thoroughly. So we can, in the center, we've got the very, very fast test cycle of test-driven development. And in between, we've got other forms of testing using executable specifications and acceptance testing and so on. We're going to try and organize our work as a series of experiments. And this is a quote from Nobel Prize winning physicist Richard Feynman. It doesn't matter how intelligent you are, if you guess and that guess can't be backed by experimental evidence, then it's still just a guess. So we're trying to aim, if we want to aspire to be engineers, to move out of the realm of guesswork and more into the realm of experiment. The next tool in my toolkit is speed. And that may sound strange as a tool, but here's a picture of a cycle time. I'm going to show you two different cycle times from two different projects that I worked on. The first one was a banking system, an order management system, and if this team followed their own development process, they couldn't release a simple line change to production in under 103 days, because that was the cost of their development process. This is a continuous delivery cycle time. This is a cycle time from a project that I alluded to into my preamble when I talked about the kind of career-changing project that I worked on. We built one of the world's highest performance financial exchanges. This project was somewhere in the order of 15 to 20 times bigger and more complex than the project on the top line, but we could make any change to our entire enterprise system and get a definitive answer on whether that change was releasable into production, meaning that there was no more work to do, and get the answer back in under an hour. That's game changing. If you work in an experimental way to reduce your cycle time, to speed up the feedback cycle in your development process, that's a tool. And that tool drives change. And it drives all kinds of different changes: behavioral changes, technical changes, organizational changes. And I would argue that if you were to take my advice and take an experimental approach to reducing your cycle time in the way that I've just described, that drives out all of agile theory, all of lean theory, all of DevOps theory, and all of continuous delivery theory. You can't have a 57-minute cycle time if your teams are too big, because the communication overhead will slow you down too much. So small teams are what we need. You can't have a 57-minute cycle time if those teams are always coordinating all of their work together for every change. So you need small autonomous teams. You can't have a 57-minute cycle time if you haven't got a great story on configuration management, automated deployments, infrastructure as code, automated testing, automated compliance, regulatory approval, automated regulatory approval as part of the deployment pipeline, security testing, resilience testing, performance testing, all as part of the pipeline. Whatever it takes to get you to a releasable outcome, which is the goal of continuous delivery. The goal of continuous delivery is that we work so our software is always in a releasable state. Even if we don't take advantage of that, that gives us the opportunity, the discipline of working in a way to high quality, making making change in small incremental steps that we validate to production quality. And that's a very, very, very effective way of working. So continuous delivery, the term comes from the Agile Manifesto, which says our highest priority is to satisfy the customer through the early and continuous delivery of valuable software. It's kind of the logical extension of continuous integration, and it's this holistic approach to software development. If you think of continuous delivery as optimizing from having an idea to getting valuable software out into the hands of users and collecting feedback from those users, that's pretty much all of software development there. So we need to worry about everything. We need to worry about how people work. We need to worry about the technology. We need to think about how organized, how the teams are structured, and all of that stuff. A good mental model for this is that every time that we commit any change, that change generates a release candidate, and the job of our deployment pipelines and our continuous delivery process is to prove that that release candidate is not fit to make it into production. Yeah, we're using falsifiability again. A single test fails anywhere in our deployment pipeline, we reject the change. And our definition of done is software being useful in the hands of users. To do this, we need to create a repeatable, reliable process for releasing software. So that means we've got to automate pretty much everything. That means that we've got to keep everything under version control, and we've got to move really, really quickly so that we can see where the pain points are, so we can take work out of the process. Continuous delivery is measurably one of the most efficient ways of doing work. We create software of higher quality at a higher rate. So you can have your cake and eat it. You can build better software faster. And that's what the data says. So the State of DevOps report and the Accelerate book say this. Studies of over 45,000 surveys representing tens of thousands of different projects, say that over a series of years. You can build better software faster if you apply these kinds of engineering techniques. And this is just me showing off. It's a quote from a few years ago. If agile software development was the opening act to a great performance, continuous delivery is the headliner. I'd now slightly rephrase that in the context of my new engineering book, which is that agile was a move away from the horrors of the mistake of assuming that ours was a production problem. The waterfall development is production lines for software, and they don't work. So agile was a big step forward, and part of agile was kind of the craft movement, the software craftsperson kind of approach. And I think that was a good step, but I don't think it's enough. I think the next step beyond that is engineering, an engineering approach. And I think continuous delivery is an engineering approach, along with the other ideas that I've been talking about today. This is a picture of a deployment pipeline, and this is in effect a machine that we use to organize our work to minimize it. So we can try, as developers, we can commit a change, we can wait for the fast feedback cycle from the commit stage to verify that the change looks pretty good from our point of view. Then we can move on to do something new, while we do take a little bit more time and a little bit more thoroughness in building release candidates, deploying them into lifelike production environments, testing their security, scalability, performance, whatever else we care about, before determining whether our software is releasable. So a deployment pipeline always goes from commit to a releasable outcome. That's what we're trying to achieve. What that means is that there shouldn't be any more work to do if the deployment pipeline says that everything's good. There's no more work to do before you're happy to release this into change. If you need additional sign-offs or more testing afterwards, it's not really a deployment pipeline. There are a variety of steps, and one way of thinking about this is that it divides into kind of 3 different phases. The first is essentially the continuous integration phase. We're looking for fast feedback that our work works alongside everybody else's work, and we aim generally to get that feedback in under 5 minutes. The next phase is what I call the acceptance phase, and this is the outcome releasable? So everything that you care about that determines the releasability of this is in this next phase. And then there's a third phase, which is really the production phase of, how do we release the change into production? How do we manage it? How do we monitor it? And so on, to gather feedback. If you'd like to learn more about this, I run a YouTube channel and I release new videos every week on topics around continuous delivery and software engineering, and all sorts of things. Lots on testing, automated testing, lots on deployment pipelines, but other things too. Do check it out. There's some useful stuff there, I think. I mentioned at the start that you can get my new book. It's available for pre-order. The electronic copy is going to be released on December the 6th, I think. But if you order it now with this code, modern SWENG, you can get 35% off the price on pre-order. So, and that's a special offer just for people that are watching my content. So this is a special offer just for you here today. That's the end of my talk. Thank you very much. I hope that we've got some time for some questions. Let me just switch back and stop sharing my screen.
Thank you, Dave. Let's see if we got rid of the echo. Hopefully.
I'll mute when I'm not talking.
Okay, so yeah, thanks a lot for the talk. Florian was busy pre-ordering, I think.
Yeah.
And
because I'm going to pre-order quite a lot because you know, maybe next year we can also distribute some. Or what's next year? What's next year? What plans do you have for next spring season?
It sounds like I'm going to be talking to your audience because you've pre-ordered lots of my books.
Definitely. So yeah, if the pandemic bears with us and it tones down, we're going to have the Codecamp Festival next year in May in Bucharest, and Dave is one of our guests there. So hopefully we can actually even have some books by that time. It's coming. All right, and we do have a couple of questions. Yeah, because of the echo, we're going to do it like we're going to ask the questions and then you, Dave, can unmute. Yeah, one thing that's, I think it's been going on for years and years. It was these two pillars, right? Testability and speed. Whenever a team is, let's say, reluctant of jumping into TDD, their biggest argument is that by doing this, we're actually sacrificing speed or velocity. How do you convince them, Dave?
Well, so this isn't how I convince them, but this is the truth, is that they're wrong. So the data says that teams that work in the way that I've just described produce software faster and with higher quality, and dramatically so. So the Accelerate book and the State of DevOps report says that teams that work in the way that I describe spend 44% more of their time on new features than teams that don't. And that's for a fairly obvious reason. If you make the mistake of skipping testing because you think that saves you time, you write buggier code. So you spend more of your time fixing bugs later. And that's a much more expensive thing. So a little bit of time now is an investment. Yes, you're going to type more at the point at which you write the code. You're going to type more characters, but that's not all there is to writing good code, typing. So at the test-driven development, I would argue, test-driven development helps me think of better designs, and therefore I'm going to do less work. That's one thing. But even if that's not the truth, even if you did the same stuff, test-driven development is at least going to say that the software works. That means that you're going to be spending dramatically less time fixing bugs in production. The data says, academic data says that somewhere around about 60% of defects in production failures are caused by the simple mistakes that all programmers put into code, whatever the language, off by one errors, conditionals the wrong way around. Those are eliminated by test-driven development. You don't get those. So that's a 60% reduction in defects just there. The empirical data is better than that. If you look at organizations that practice continuous delivery, they usually report somewhere close to 2 orders of magnitude reduction in defects in production. Paddy Power, the sports betting company, when in their first year they reported a 97% drop in defects in their first year in production. Think about having 97% fewer defects that you need to diagnose in production, triage in meetings, and then schedule through tickets in Jira or whatever. All that work goes away, and so you win that back. So overall, test-driven development is measurably, dramatically more efficient. It just doesn't feel like it at the time. So it's rather like not doing the testing at the point at which you write the software is rather like deciding that you're going to save time by not brushing your teeth. Sooner or later, your teeth are going to fall out.
Yeah, well put. Yeah.
Let me smile a little bit. So you mentioned about Betfair, and their, dropping defect, and so I understand that after TDD, the right winner was chosen, or okay.
And I had another one. Hope I'm not going to open a can of worms here, but in terms of continuous delivery and gaining more speed, how do you feel about feature branches versus trunk-based development? I know this is another one of your favorites.
I have two of the more popular videos because they're argumentative on my YouTube channel. Don't branch, and I said don't branch. so I think I can make a reasoned argument why feature branching and continuous integration are opposite to each other. Continuous integration is designed to expose changes. The inventors of continuous integration, of the term anyway, in the late 90s, the people that invented extreme programming, described it as, imagine sitting working at your computer and making a change, and instantly that change was visible to all of your teammates. That's continuous integration, and we can't quite achieve that, so it's not quite continuous, but we're trying to integrate our changes together as close to continuous as we can get. What does integrate mean? So one of the pushbacks that I get from people that like feature branching is, well, okay, I'm going to pull from master all of the time, from trunk all of the time onto my feature branch, so that's integrated, right? Well, no. If us three are all working on code and we've all got code on separate feature branches, there's nothing interesting going on master or trunk because it's all going on our feature branches. So I can pull as much as I like. I'm not going to get your changes. I'm never going to see them. So I can be doing things that are going to kill your software, and you don't get to see them until we think we've finished, and then it's too late and we merge them together. There's a big cost to that. The real answer is not my opinion or any of this kind of stuff. It's the data, and the data says is that the teams that use feature branches that don't, I'll slightly rephrase. Continuous integration is, in definitional terms, is merging everybody's changes together at least once per day. So if you have a feature branch that lasts for longer than a day, you can't do, by definition, continuous integration. So if you have feature branches that last for longer than a day, then the State of DevOps report says that you create lower quality software slower. You have more bugs in your software, and the rate at which you produce that software is slower. So feature branching is not my favorite way of doing things. I can understand why it's appealing. There's part of me that wishes that it was true, that it worked better, because it would be a nicer way of working in some ways, a simpler way of working in some ways. But the truth is that it isn't. It isn't a simpler way of working. It's a more complex way of working, and it's a more dangerous way of working because you're exposed to the danger that you're going to hit some nasty merge. I'm going to do something horrible that causes you a load of work that you hadn't thought of. And that's always true. Whether you get away with it or not, that risk is always there. That could always happen. And it can always happen in continuous integration, but because we're integrating continuously, it's going to be 5 minutes worth of work rather than 5 weeks worth of work or 5 days worth of work.
All right.
Or at least you find out your issues sooner, and that's always better.
Exactly. It's about this working in small steps and just these little increments. It changes the way that you have to work. There's some more detailed stuff on my YouTube channel. If you watch the videos, Don't Branch, or I said Don't Branch on my YouTube channel, it goes into different aspects of this and the different consequences of what that means.
Indeed, yeah. So, well, yeah, I'm a big fan of your channel, and I think people out there are as well. Once again, Dave, thank you very much for being here again with us. I think I forgot the count, and we hope to see you next year again.
May the 19th.
Great.
Looking forward to that.
Great. It's a pleasure. Thank you very much for asking me. Thank you, everybody.
Have a nice day. Thank you so much. Until next time.
Bye.
Thank you, Dave. We're going to take a short break. I think we have exactly 5 minutes, and then we're going to regroup here with the next session. See you soon, everyone.
See you.